directly. So this was the concept. Let us understand the limitation of this XOR phase detector through its transfer characteristics. So same waveforms, just for the reference, it is replicated here. Okay. Output is directly proportional to the phase difference. Let us plot the transfer characteristics. So what is the transfer characteristics? It is the relation between output and input. What is the output in phase detector? Output is going to be a voltage. And what is the input? Input is going to be a phase difference. So let's plot the transfer characteristics. So here you see the transfer characteristics for XOR as a phase detector. So on x-axis we are plotting phase difference. On y-axis we are plotting the total voltage. We provide VCC as a power supply to the IC. So as you see, the voltage can change between 0 to VCC. So when phase difference is 0, obviously the voltage at the output of XOR gate will also be 0. So there we can say that both the inputs are perfectly locked. Now whenever unlocking happens, there will be a phase generation, phase difference, and that's why output will be generated. So as you see from the characteristics, as the phase difference increases, the output also increases. But how long this will continue? What will be the maximum output that you can get? Now maximum possible phase difference which can be generated in this case will be when both the signals are 180-degree out of phase of each other. That means for on time, if you have off time here, and for off time of input 1, if you have on time of input 2 here, you can say that they are 180-degree phase shift. That means the phase difference will be pi. So in that case, you will have the maximum output generated. So that's why, as you see here, for pi phase difference, it will be maximum. And later, if you again delay the second input and try to shift the waveform further beyond 180 degrees, again the phase difference will reduce. Okay, so after pi, as you see, output again falls, and finally when phase difference becomes 2 pi, again both the signals will overlap each other. It is just like in phase condition, and that's why output of phase comparator will fall down to 0. So hope you have understood the concept of phase detector. So I repeat, phase detector is to detect the phase difference between two inputs. We generate the proportional voltage. The voltage output is proportional to the phase difference between two input signals. So let us move on to the next concept, which is also very essential and very important. Voltage controlled oscillator. Popularly, it is abbreviated as VCO. Now, when we see the block diagram of PLL, there you will find this VCO as an integral part of PLL. In a way, in voltage control oscillator, we convert voltage to frequency. So in short, we can call it as a V2F converter. Just like we have seen voltage to current converter, current to voltage converter, analog to digital converter, digital to analog converter. So like that, we have frequency to voltage conversion and voltage to frequency conversion. So voltage control oscillator, we can even view as a voltage to frequency converter. So let us understand the concept of VCO. So here how you can define VCO. So it is an electronic circuit which converts the voltage into frequency. So this is just to emphasize the concept of voltage to frequency conversion. So we can call it as voltage to frequency converter. But another useful definition which we require in PLL is that VCO is basically the circuit in which the output frequency is a function of input voltage. So we are giving the voltage, we are changing the voltage, and we are trying to control the frequency of oscillations. So here one thing you should understand, if you look at the title, that is voltage controlled oscillator, basically it consists of an oscillator. What is oscillator? Oscillator is a circuit which generates the oscillations without any input. Actually, even though we don't give the input, we have a power supply. So we are providing a DC energy through the power supply, and that DC energy gets converted into oscillations, that is AC energy. So although we don't give the input, there is always a conversion of energy and we get the oscillations. So in oscillator, we say that without any input, we get the output oscillations. Now in oscillator, you must have seen that every oscillator has got its own frequency, which depends upon a timing components, and most of the times we see that the timing components are resistance and capacitors. So one oscillator we have studied in our course in the comparators is square wave generator. So there we have studied that output frequency is a function of feedback resistance and the capacitor in the circuit. So try to understand that in VCO also, basically it is an oscillator, and that's why it will have its own frequency, and that frequency we can change with the help of external voltage that we are going to supply to the VCO. So that's why we call it as a voltage controlled oscillator. So let us understand the concept very quickly. So as I was talking about the frequency of oscillations, so every VCO will have its own frequency based on its resistance and capacitance. We call that frequency as a free running frequency. And the notation here we are using is F0. So try to understand that when we don't give any external voltage, this VCO will be freely running. Freely running means what? It is freely oscillating with its own internal frequency, which is dependent upon its own R and C components. So that frequency is called as free running frequency F0. Now with the help of external control voltage, we intend to change this oscillation frequency. So how we do that? So here is the block diagram. So as you see here in VCO, if you see the output equation, so output frequency is equal to free running frequency plus this is the transfer function of VCO, or we call it as a gain of VCO, multiplied by control voltage. So in oscillator, normally we don't have input, but here we are deliberately providing the external control voltage. This is not the input, but this is a control voltage that we are providing, which will change the output frequency. Okay. So let us understand the transfer characteristics of this VCO. So if you plot transfer characteristics. On x-axis, we are plotting input as control voltage. On y-axis, we are plotting the output frequency. This is the equation. So what is the meaning of this? So as you see here in the transfer characteristics, when control voltage is 0, so there is no voltage given from the outside. So VCO, output frequency, will be equal to F0, which we call it as free running frequency. Now since control voltage is 0, that's why this factor will be 0. So you will have F out equal to F0. So as you see here, at 0 frequency, 0 control voltage, the output frequency is F0. Means the voltage control oscillator will oscillate with its own frequency, which is its natural frequency, and that is dependent upon its timing capacitor and resistance. Here in the block diagram, I have not shown the resistance and capacitor, which are the timing components, but through these timing components later in the design, I will show you that we can set the pre-running frequency. Is that clear? Yes. So as you see here in these characteristics, at 0 control voltage, you have output frequency as F0, and later as control voltage increases, the output frequency also linearly increases. The slope of this characteristics is basically a conversion gain. So more this factor, you will have more this slope. So what will be the unit of, or what will be the unit of this KVCO? Can you find out? So it is F out divided by V control. So it is F by V. That means it is frequency by voltage. Okay. So gain of this VCO will be simply output frequency divided by control voltage. Fine. So thus VCO basically converts voltage into frequency, or we can say that we can change the frequency of VCO below or above F0 depending upon the control voltage.